Hello, my name is Dr. Mark Abelins. This is a brief, very informal video intended exclusively for use in my Geology 1030 sections 7 and 8 during fall 2014. This is a video about plate tectonics. Its primary purpose is to explain key plate tectonic concepts. The answers to several plate tectonic study questions will be in this video. As with all parts of the course, it's good to go to the notes and read the takeaways. First, thanks to GPS and other technologies, plates and plate motion are now observational. They're essentially factual. That said, some aspects of plate tectonics may always remain theoretical. Plate tectonics explains the origin of Earth's features as well as most contemporary earthquake and volcanic activity. While the contemporary theory of plate tectonics emerged during the 1950s and 60s, it was preceded by Alfred Wegener's continental drift hypothesis in 1915. His hypothesis had many of the key elements of plate tectonics, but it was rejected by most scientists in his day. Then, during the 50s and 60s, a lot of technological innovations led to really a new view of our planet, and in particular the ocean. This new view caused scientists to dust off Wegener's idea that the outer part of the Earth was mobile, to fix what was wrong with his idea and the ideas of others from that time, take what didn't need fixing, put it all together, create the modern theory of plate tectonics during the 50s and 60s. Heat transport, including most especially mantle convection, is ultimately behind the movement of the outer part of the Earth. And then in detail there are three forces: slab pull, ridge push, and mantle drag. Okay, let's check out these study questions. The other thing that you should do always, and here in the introduction, which is what I'm giving you, is it possible to measure plate motion with GPS? And the answer is yes, it is. Here is a slide that came from the publisher, Pearson. Those red arrows that you see on this slide, those arrows are showing you the direction and the rate of movement of the major plates. Here's a key right here. So, are we talking meters per year, kilometers per year, centimeters per year? What would be the best units to use to measure this or describe this? You tell me. You can see what's on the screen. Pretty slow movement, kind of the rate at which your fingernails grow. The plates themselves, there are about a dozen big ones, and you see them here on the map. They are separated one from another by big faults. San Andreas Fault in California, you've probably heard of it. That would be an example of the principal fault at one plate boundary. In that case, the boundary between the Pacific plate and the North American plate. We can measure these movements, one plate moving relative to another, the plates moving. We can measure that using GPS, the Global Positioning System. You have it on your phone. You have it perhaps in your car, boat, airplane, if you're in aviation. Now, the GPS on your phone tells you where you are to within a few feet, which is not going to be good enough to measure plate motion. But scientists have GPS antennas that are very firmly attached to the solid rock of the Earth. They can also have knowledge about where the satellites, the GPS satellites, are in their orbit, very precise knowledge about that. The scientists can also correct for atmospheric effects. And by doing a lot of computer work with the signal that comes from the GPS satellites, scientists are able to do a lot better than a few feet, which is what your phone is giving you, your location to within a few feet. Scientists can do a lot better than that. Indeed, they can do good enough to measure plate motion, what's shown by the red arrows here on this map. Next study question. Are plates the same things as continents and oceans? For example, is the North American plate the same thing as the North American continent? Is the Pacific plate the same thing as the Pacific Ocean? The answer to those questions is no. Continents and oceans, not exactly the same thing as plates. Let's look at this map again. Okay, here's the North American plate. It's this whole shaded area. And yes, it does include much of the continent of North America, but it doesn't include all of the continent of North America. Also, the North American plate includes a big amount of seafloor underneath the western part of the Atlantic Ocean. All of this right here, seafloor, is part of the North American plate, but it's not part of the North American continent. So, continents, plates, not the same thing. Hard to see on this map, but the south coast of California, the central coast of California, they are on the North American continent. Yes, Southern California, central coast of California are part of the North American continent, but they're not part of the North American plate. On what plate are they located? They're located on the Pacific plate. South coast of California, central coast of California, part of the Pacific plate. Part of the North American continent, but part of the Pacific plate. So, continents, not exactly the same thing as plates. It would have been good if separate names had been used. North American only applied to continent, but not also to plate, since they are not the same things, the North American continent and the North American plate. But there you have it. A little bit confusing. You guys can handle it. I know you'll do well with this. And then, like Pacific plate, okay, not exactly the same thing as the Pacific Ocean. And you can see that on the map as well. Yes, much of the Pacific Ocean is sitting on top of the Pacific plate. There's also a plate over here. It's called the Nazca plate. This plate right here off the west coast of South America. The Nazca plate is sitting underneath the Pacific Ocean, but it's not called Pacific plate. It's called Nazca plate. This plate right here. Not the same thing. Continents and plates or oceans and plates. Okay, let's see what else is in the study questions. Oceanic and continental crust. The differences between those. Okay, you guys learned crust, mantle, outer core, inner core. You guys know all that. You guys are on top of that. You guys are going to rock on that exam on September 16th. But there's more. Crust, mantle, outer core, inner core. Yeah, that's quite a bit right there, but there's more. Oceanic crust versus continental crust. Okay, well, you tell me. Okay, looking at these two, which one is thinner, which one is thicker? Let's start there. Oceanic crust is thinner. Continental crust, it is thicker. But it doesn't stop there. In lab, if you haven't done so already, soon you'll be getting into a box of igneous rocks. The oceanic crust is like the igneous rocks basalt and gabbro, pretty much throughout. The rocks and the minerals of which they're made the rocks and the minerals that make up the oceanic crust, they're relatively rich in iron and magnesium. They're what are called mafic. Mafic minerals there's quite a bit of them in these rocks. They're kind of richer in those things, kind of poor in silica. In contrast, the continental crust is thicker, but also the upper part of the continental crust, it's like the igneous rock granite. Igneous rock granite has more silica-rich minerals in it. The minerals has fewer of the iron and magnesium-rich minerals, more of the silica-rich minerals. Those are called felsic minerals, more of those. Silica-rich, poor in iron and magnesium. If you have to pick a rock to represent the upper part of the continental crust, pick granite, that one. Now the lower part of the continental crust, it's more like basalt or gabbro, and it is mafic. It has more of those minerals that are rich in iron and magnesium. That's the difference between oceanic crust and continental crust. Okay, more study questions. Lithosphere, asthenosphere, which is relatively warm, which is a solid that flows, which is relatively rigid. Is the lithosphere just the crust and all of the mantle, the crust and part of the mantle? Where is the asthenosphere? For example, is it in the lower mantle? Again, you guys learned crust, mantle, outer core, inner core, but there is more to all of that. I know this figure is kind of busy. It's in Chapter 1. For example, inside of the Earth, and there's the inner core, there's the outer core, there's the mantle, and then the crust is this thin rind on the outside. Okay, but there's more. Lithosphere and asthenosphere. The lithosphere, put simply, as shown here, it is the crust, oceanic crust, continental crust, whatever crust it is the crust and the uppermost part of the mantle together. Crust and uppermost part of the mantle together, that is the lithosphere. It is all of the crust, but just the uppermost part of the mantle. Now, crust, mantle, they're made of different things. They're different in many ways. So why have a name, lithosphere, that includes both? What it is that the lithosphere is relatively cool. It is relatively rigid. In contrast, the asthenosphere, that's right below the lithosphere, it is warmer, it is plastic, meaning that it flows. I don't mean that it's plastic like you make a toy car out of plastic. It's rock, but it's plastic in the sense that it flows over time. It flows at rates of like 5-10 centimeters per year. And in places, it's a little bit liquid. Now, it's mostly solid. It's a solid that flows, like Play-Doh, silly putty, or glacial ice. But in places, the asthenosphere has melt in it. Small amounts, like 3%, 5%, something like that. The asthenosphere, as you can see in this illustration, is located in the upper mantle. But it doesn't include the uppermost mantle. Uppermost mantle, along with crust, is part of the lithosphere. But a big part of the rest of the upper mantle is taken up by the asthenosphere. Warm plastic, flowing at rates of 5 to 10 centimeters per year. Few percent melt, 3%, 5% melt in places. But it's solid rock. It's a solid that flows. As I said, kind of like silly putty, Play-Doh, glacial ice. Other study questions? think I mentioned some typical plate motion rates. So I think for the introduction, you now have the information that you need.